Good morning. So this is our last lecture class. So we might have a photo op at the end of the lecture today. So the next 2 weeks, you will have a third exam on Monday, next Monday, and then the final exam on next Monday. So the last topic that we have is electrochemistry. Okay, so this is not new to you. You have tackled already this last time in your Gen Chem 2. And if we're going to look at electrochemistry, it's just more on the redox reaction. Okay. Now, if we're going to what we call look at the fundamentals of electrochemistry, there's a lot of contribution that we have for electrochemistry. Okay. If you're going to look at the everyday materials that we have, there's some electrical measurements of different chemical process, and usually it's at the surface of an electrode. Now you may ask yourself, when did you experience doing electrochemistry? When you're taking the pH, that's a classic example of electrochemistry. The one that we're going to do this week, the measurements of fluoride, that's electrochemistry. If you have parents or relatives that are diabetic, the sugar meter that they have there, that's also an application of electrochemistry. Okay, so electrochemistry, if we're going to look at this, there are a lot of applications in terms of the electrical measurements of chemical processes at the surface of the electrode that can serve in analytical chemistry. So if you're going to look at the term that we have here, so you will have current, voltage, ampere, okay, coulomb, and there is an associated methods to it. So for instance, if you have potentiometry, this is just an analytical method in which an electric potential difference, which is your voltage, okay, of a cell is measured. So potential difference, that's why you have the potentiometry. Okay, and then you can also have voltammetry. So if you're going to look at the root word of voltammetry, it's what? Voltage. So this is in relation between the current and voltage is observed during a reaction. Okay, so potentiometry, if you're going to look at this, it's a method where voltage is measured. So you measure voltage here. Now for that voltammetry, what you're looking at is the current and the voltage that is applied. So that's the difference between the two. Okay, you can also have amperometry. So if you're going to look at the example here, what you have here is your pH meter, the fluoride sensor that you're going to use this week. For voltammetry, usually the one that you have here are the stripping analysis for heavy metals. Now, for amperometry, on the other hand, the classic example that you have there is your sugar meter. Okay, so in amperometry, you look at the measurement of electric current. So ampere is the root word. Ampere is the unit of what? Current. Okay, and then you also have coulometry. So this is under coulomb. So coulometry, if you're going to look at this is a technique in which the quantity of analyte is determined by measuring the number of coulombs. What is coulombs? Anyone? It's the charge of what? No, it's the unit of charge. The charge of what? Okay. So coulombs is the unit of charge. So these are just some. And if you're going to look at this, all of them is under redox. Okay. Oh, before we still have this electrogravimetry. Or electrogravimetric analysis. So this is a technique in which the mass, okay, of an analyte is used to determine the quantity of the analyte. So when you have electrogravimetric analysis, the mass of an electrolytic deposit is measured for complete reaction. So these are just some of the technique that is associated with electrochemistry. So last time, I think, I'm not sure, if I introduce you to this concept of Leora and Geroa. Okay? Because that's the basic of redox reaction. So redox reaction is just transfer of electron. So if we're going to look at this, so this is a reduction. So what does this mean? So if it's a reduction, I would say it's in the Geroa. So it gains electron, undergo reduction, and oxidizing agent. Okay. Now the other one that you have there, that's your oxidation. So if you're going to lose it, that's lose electron, oxidation, and reducing agent. So what we have here is a redox reaction. So if you're going to look at this, this is your reducing oxidizing agent, and this is your reducing agent. Now, you may ask, how much do you have here? So, okay. So how much charge is involved there? So you are introduced to this concept of the Faraday constant in honor of Michael Faraday, who revolutionized the study of redox reaction. And how do we determine this charge? Okay. We just multiply the number of moles that we have with the Faraday constant. So for instance here, How are we going to solve this? If 5.585 grams of Fe3 plus were reduced in the previous reaction, how many coulombs of charge must have been transferred from vanadium 2 plus to Fe3 plus? So how are we going to do this? So you get the equivalent moles of this and then multiply it with Faraday constant, because the Faraday constant tells us the number of charge in a given coulomb. So if we're going to solve this problem, we just have what? 5.585 grams divided by 55.85 grams per mole. What is 55.85? Anyone? What is 55.85? Anyone?
0.1.
Huh?
0.1 moles.
No, where did I get that value of 55.85? Anyone can tell me where I get it?
What's the molar mass, right?
Okay, so that's the molar mass of your what we call Fe. Okay, so if we're going to look at it, that's the one that we need so that we can convert our materials or our numbers into the number of moles. Okay, so what we're going to do is we're just going to multiply it with the Faraday constant, which is 96,484 coulomb per mole. So this is what we call cancelled, and this one is cancelled. So what's the value that you have? I just need to get my calculator. What do I get? Okay, so 9.6 coulomb. Okay, so that's the simplest calculation that we have here, wherein we're given the grams and we are asked how many, what's the charge that we have there. So question. So when we're talking about electric charge, which is the Q, okay, electric charge is just measured in coulomb. So what does it mean? 1 mole of electron has a charge of 96,484 coulomb. And if you're going to look at this unit that you have here, the coulombs per mole, the other term that they have there is a Faraday. So the first thing that you have, Q equals to N times F. Okay, so the next thing that we need to do is this one. Suppose that electrons are forced into a platinum wire immersed in a solution containing tin 4 plus, which is reduced to tin 2 plus at a constant rate of 4.24 millimoles per hour. How much current passes through the solution? So we're talking about here now current. So earlier we talked about charge. Okay, so how are we going to solve this problem? So maybe we can write the reaction. So the reaction here would be what? Where is the 4 plus and where is the 2 plus?
The 4 plus is on the left, 2 plus is on the right.
Okay, the 4 plus is your reactant and the 2 plus is your product. Now where's the electron? Where will I put the electron? Will I put it here or will I put it here?
Left.
On the left side.
Left side. Okay, so this is the reaction. So it says there the amount of tin 4 plus that is reduced to tin 2 plus is 4.24 millimoles per hour. And in that case, we have 2 electrons that is involved. So if we're going to solve this one, okay, so what does this mean? We're going to multiply by 2 the given rate that you have there. Okay? And then what do we need to do? So you have your 8.48, right? So what's the one being asked? Current. Okay? So if we're going to look at the definition of the current, that's the quantity of charge flowing each second through a circuit. And the unit of current is ampere. Anyone know what ampere is? So they said this current is the charge that flows through time. So this is your ampere. Coulomb per second. So that is the ampere that you have. So we have a lot of multiple choice question that can be obtained from today's lecture. Okay? Or supply the missing answer. So these are the Blackboard questions that you can expect. So the one that is being asked now is how much current passes through the solution. So what do we have now? We have now the number of moles of the electron. So what do we need to do with this? So this is the amount of the electrons per hour. So if it's a current, we need it to end with this unit. Okay? So what do we do? What's the next thing that we can do here? Can we say we convert this to what? For every 1 hour, you have 3,600 seconds. And then what? Whatever we get there, for every 1 mole, you have 96,484 coulombs per moles of electron. So what do we need to do to change here? Maybe this one, because we have what? Millimole. So make sure we can put another one there wherein we convert the millimole to moles. Is this okay? Can you double check if my arrangement is right? Or maybe what I can do is I can do the calculation first here, so I end up with the millimoles per second, and then from that I can convert them to So this is 1,000 millimole and moles electron. Because I need the unit to be C over S. So if ever I do it, I cancel this out, I cancel this out, I cancel this. Yeah, so I have C per second. So what's the answer? So you have there 0.227 ampere. So question. Now, if you're going to look at the stuff that we're talking about, you may say you might be in the wrong course because mostly this stuff are discussed in what? What course? Anyone? Maybe some of you took already the course where this is usually discussed. Okay? So you might ask yourself, why are we discussing this stuff? This stuff should be discussed in what? Physics. Okay? But we're discussing it here because as I told you, the basis that we have here is the redox reaction. So to at least help us understand what is this current really is, so we could say electric current is analogous to volume of water per second flowing, okay, out of a hose. And how do you differentiate current from potential? So electric potential is analogous to the hydrostatic pressure, pushing water through a hose. So high pressure gives high flow. Okay, so there's the difference that you have between potential and current, because usually we often use them interchangeably, but if you're going to look at the meaning, they're not really the same. Okay, one has something to do with the flow, while the other one has something to do with this what we call pressure, and the pressure has something to do with difference. So what else that we have term that we can have here aside from this? So later on, we can have resistance, we can have other stuff. But what we can look at here is potential is a little bit relative. So we go on what we call another step. So what we have discussed so far is just voltage. Voltage is your potential. So how is it relate with work and free energy? Okay. So if we look at this voltage, we look at the potential difference. So between this is between 2 points. And how do we define work? What's the basis that we have here for work? So work is just equals to this. Potential difference, or the one in the voltage, times the charge. And you can be asked this question, how much work can be done if 2.4 millimoles of electrons fall through a potential difference of 0.27 voltage? So let's try to look at voltage, work, and free energy. Okay, so they said potential difference between 2 points is the work needed when moving an electric charge from one point to another. What's the other definition of work? Anyone? The more simpler, or the simpler definition of work. Anyone? Work is equals to what? Work is equals to, are you familiar with this one? Work is equals to force times distance. Okay. Now you may ask yourself, is this applicable in chemistry? Force times distance. That's why they said if you're sitting all day, you're not really doing work, because the definition of work is force times distance. So there should be a movement. Now the question is, how are you going to apply this in a chemical system? Okay. So you apply work in the chemical system by looking at the movement of the electron. So the way that they look at it is they look at the change in the volts. Because Coulomb will always be the same. Okay? So the potential difference is the one that's going to change the value that you have here. Why did I say Coulomb would always be the same? Because this is always your what? Faraday constant. Okay? Now, the thing that you have here is you just need to convert the Q that you have here. So Q is equals to what? N times F. So once you have a specific amount of moles, that value will be constant. This all you need to do is you multiply it with your Faraday constant. Now, E is already given here. So if we're going to solve this one, you will end up with 2.4 millimoles. What is its equivalent in moles? Anyone?
Divide by 1,000.
Huh? Divided by 1,000. So that would be 2.4 times 10 to the negative 3, right? So if I'm going to get this Q first, so 2.4 times 10 to the negative 3, and then multiply it with the 96,484. C for moles. And I can use it here. And I have to multiply it with 0.27 volts. So what's the number that we have from here? So the unit will be charged. So that will be giving you what? What value do you have? So the value that you have here is 231. So I can make it 2.3 times 10 to the 2. So what do you get when you multiply voltage with C? So what's the number that we have here if we what we call multiply these two? So you have around 62 or 63 joules. So that's the answer that you have. How much work? So if you're going to look at the unit, you may ask yourself, why is it in joules? So if you're going to look at the thing that you have here, so you have volt, multiplied by coulomb, you have the joules. Analyze. How did you end up with this one? Why did you end up with joules? If you're going to look at this, what is voltage equal to? Anyone? How did we end up with joules as the unit? So if we're going to look at voltage, voltage is really joules per coulomb. So joules per coulomb times coulomb will give you what?
Joules.
Joules. Okay. So I just want to show you that this doesn't come out of nowhere. So there's a corresponding we could say unit that you can look at. So the equivalent of joules is I mean the unit volt is equivalent to joules per coulomb. So joules per coulomb times coulomb will give you joules. That's why you end up with that unit. Now, synonymous to this also is the free energy. The free energy is work done on the surrounding. Okay? So if you're going to look at delta G at constant temperature and pressure, for a reversible reaction, okay, we'll just let it pass. Okay, there we go. So if we're going to look at this one, if delta G, which is your free energy, at constant temperature and pressure for a reversible reaction, that is equals usually to the mass. The electrical work that can be done by the reaction. So work done on the surrounding is negative delta G. Now, if you're going to look at its definition, it's just the negative of your work. Okay? So, you know from your Gen Chem, I hope you remember this, the definition of that the delta G is negative of moles times the Faraday constant times the potential. Okay? So if you're going to look at the relation between the delta G and the electrical potential difference here, a positive potential signifies you have a spontaneous reaction, which gives you a negative delta G. I don't know if you still recall that thing. So if you have a negative delta G, you're going to have a positive delta E. So both of them signifies that it is spontaneous. How do we define spontaneous concept? So this is Gen Chem 2 that we're talking about today. So how do you define a spontaneous reaction or a spontaneous process? Anyone?
The reaction happens without external energy being added to the system.
Okay. So when we say spontaneous reaction or process, it happens on its own. Okay. So classic example that I gave to my student of a spontaneous process is failing a course or failing a class. Because you don't do anything, how do you think you're going to pass the course? Okay, so failing a class or failing an exam is a spontaneous process. So how are you going to prevent failing an exam? You have to study. So that is the outside intervention that you have to do. Okay, because spontaneous process, you don't do anything, it will happen. And if you're going to look at the history, how they come up with the spontaneous process in terms of thermodynamics, Gibbs free energy is related with what? What term that you learned first, one of them in Gen Chem 1 and the other one in Gen Chem 2. So if you could remember, it's related to delta H and delta S, enthalpy and entropy. Okay? So because before they tried to determine how do we know if a reaction is spontaneous. So they found out some exothermic reaction and endothermic reaction are happening spontaneously. So they need another physical quantity. And that other physical quantity has something to do with the degree of disorderliness. So they found out in most spontaneous reaction, okay, disorderliness increases or orderliness decreases. So when you combine the two, I don't know if you still remember this, delta G is just equals to delta H minus T delta S. So there's your free energy. Okay. So another thing that we can relate delta G is in terms of electric potential. Now, in addition to that, we also have this P. What do you think the P here? So we have a little bit of P6 this morning. P is equals to power. And if you're going to look at the power that we have here, they said this is just work per second. Or EQ, E times Q per second. Okay? So what do you think is the unit of power? What do you think is the unit of power? Anyone?
Joules per second.
Yeah, but what do you call that?
Watts.
Okay, so the unit of power is watts. Where do we hear that term? Anyone?
They put it on light bulbs a lot.
Okay, so you use it in light bulbs. So you have there what? 50 watts, 100 watts, 150 watts. But the one that they have right now, the energy saving thing is just around what? 30, 40, 50 watts. So if you're going to look at power, we could say that's the efficiency of work. The higher, the more efficient it is, the higher the wattage of these materials. Okay. Another way of looking at the power is this one, E times I. Okay. Where did we get this I? This one. And your I is, what do you call this? Anyone?
Current.
I'm still grading you for your quiz. That's current. So you might ask, where did we get that I? That's just the equivalent here. Okay, so if we're going to look at this, we're we're now going to current. We need to know additional thing about that thing. Electricity. How current is used in electricity. So current is just defined as charge over time. Okay. So coulomb per seconds, you call it ampere. Now let's say you have this information here. So this is a battery that has a potential of 3 volts and a resistance of 100 ohms. Now you are asked to find the current and power delivered by the given circuit. Okay? So you are introduced here to another equation known as Ohm's law. So Ohm's law is just equals to potential equals to current times resistance. So if you're going to look at here, this is just potential equals to current times resistance. So you are asked here now, find the current and the power delivered in the given circuit. So if we're going to rearrange this thing, we're going to get the current, right? And once we get the current, we can determine the power. So how do we determine the current here? So we divide both sides by R. So I is equals to E over R. So what is the E? 3 volts divided by 100 ohms. And this is equals to what? Anyone who have not answered yet? So you can have a grade in your quiz. So this is equals to 0.030 ampere or 30 milliampere. Now, how do we multiply for the power? So we go back to our definition of power in the previous slide. So power is just E times current. And we determine now, based on what we have here, 0.0 P equals to E times I. So all we need to do, you have 3 volts here times 0.030 ampere. So if we're going to break down here, so this is what? Joules per current times current per second, right? This is the unit that we have here. So this is joules per second, or what? So 3.0 times 0.30 will give you what? 0.09 watt. So those are the type of calculations that you have in your exam next week. Now you may ask yourself, what is Ohm's law? I think I have the next slide that I have here, a picture. Oh, I don't have it here. Okay. This is on how what we call the Ohm's law is related. I'm trying to find the thing there. So what have we discussed so far? So we discussed charge, okay? We discussed voltage, and then we discussed current and how we use it in our what we call chemistry. So the next thing that we're going to do is just a review of your Gen Chem 2, the galvanic cell. So if you're going to look at this galvanic cell, okay, this is just your battery. What's the definition of your galvanic cell? Try to recall your Gen Chem 2. Those who have not answered yet. What can you say about this? Usually it is spontaneous. What can you say about its potential? What's the sign of the potential if you have a galvanic cell? Hmm? What is usually the sign of your potential? Is it positive or negative sign if you have a galvanic cell?
Positive.
Okay, it's always positive. Your galvanic cell, okay, the other term that you have there is voltaic cell. And if you're going to look at this, these are just a derivative of Italian name. Okay, you have Alessandro Volta and Luigi Galvani, the one who made studies of these galvanic cells. So if you're going to look at the galvanic cell or voltaic cell, they use as a spontaneous reaction to generate electricity. So you have a redox reaction here. One reagent is oxidized and the other is reduced. They are physically separated. Okay. And the electrons are forced to flow in an external circuit. So if you're going to look at this reaction here, you can be asked the question, what is the anode and what's the cathode? How do we define the anode? Anyone? So this is just Gen Chem 2 review. How do we define anode? What's the role of the anode?
It's the positive charge.
Huh?
It's the positive charge.
Is it the positive charge? Or what reaction happens in the anode?
Oh, well, the positive charge flows to the anode.
Okay? Because usually the anode and the cathode, they are just the electrode. And in the electrode, that's where the reaction takes place. So what happens in the anode? And what happens in the cathode? So there's only two reactions there, right? You have the redox reaction. So which one happened in the anode and which one happens in the cathode?
In the anode, the oxidation is occurring.
Okay, so usually if you're my students, I ask you vowel to vowel, consonant to consonant. So the anode is where oxidation takes place, whether it's a galvanic cell or an electrolytic cell. Cathode is where reduction takes place. So if I'm going to ask you this question here, what happens in the anodes? Usually you're going to write the reaction that is oxidation. And which one is oxidized between here? If we're going to write the reaction for this cell, how will I going to put it here? How does the oxidation reaction looks like? Anyone?
Lose electrons.
It loses electron, yeah. But how does the reaction looks like? So if you're going to look at this, so you have here copper. So what happened?
Copper 2 plus.
It became 2
electrons.
plus and 2 electrons. So the electrons being in the product tells us that it was lost. Now, cathode, on the other hand, you have a silver ion reacting to get the electrons that was gained to give you a silver metal. And if you're going to add them together, so you can just put 2 here, 2 here, and 2 here. So this is the overall reaction. I don't know if you still remember this. Okay, so let's discuss some of the galvanic cells. So this is how a typical battery looks like. And this is the overall reactions that you have. So you always have a zinc metal in your battery. And that zinc metal, that's the one that is usually oxidized. Okay. And then this is the one you have in your car. So it's some sort of a reversible one. Okay. So when you discharge, this is the reaction. So what happened if you battery stop? You just have to recharge it, and once again, it will what we call generate electricity. So if we're going to look at this redox reaction, as I have told you earlier, they should be in separate places. So what happened here? When you have a cadmium reacting with a silver. So this is the reaction that you have. So silver chloride producing silver and chloride ion, and then cadmium producing cadmium 2 plus. So if you're going to look at the overall reaction, this is what you have. Now the question that you can be asked here is this possible? Is this reaction possible? At least for this one, okay? I want you to look at the difference between the two cells. So one has silver chloride. The other one doesn't have anything. So there's a difference between the two. Now for the first one, we could say the reaction happened. Why? Because you have a silver chloride in the system. So what happened? That's the one that participates in the reaction by showing you here. Okay. So if you're going to look at the reaction, this is what you have. Silver chloride producing silver metal and chloride. Now what happened if you remove that silver chloride like this one? So this is the reaction that you have. And unfortunately, it don't happen spontaneously. Okay. So that's the difference that you have here. Why? Because your silver can go in either direction. Unlike in the previous one, okay, you can see that you don't have a silver ion. Your silver ion is in the solid form. It doesn't dissolve. How do we define silver chloride? Will it dissolve in water to give you this? Recall your solubility rules. All chlorides are what? Okay. All chlorides are soluble except silver, mercury, and lead. So you don't have silver ion here. But if you're going to remove that silver chloride and instead what you have? A silver ion, you don't going to have a galvanic cell. Okay. That's why you have an X here, which tells us that this reaction will not take place. Okay. Now, this is the typical voltaic cell that was shown to you when you are in Gen Chem 2. And what's the role of your salt bridge? Anyone? Anyone?
Can you
What is
repeat the
your salt
question?
bridge? Huh? What,
Sorry, I
what,
said, can you repeat the question?
what's the role of the salt bridge? What does the salt bridge do? Is it the one that enables the flow of ions? So if you're going to recall your voltaic cell, so you have an exchange of electrons, right? One lose an electrons and the other one lose an electron, the other one gains electrons. So if this is the one that's lost electron, what happens to the charge on this side? You lose a negative charge, so this become what? What charge? This area here. They become positively charged. And this one, since they gain electrons, they become negatively charged. So the role of your salt bridge is to make sure, maintain the electron neutrality. So look what happened here. This is a positive charge, so the negative charge of your salt bridge goes here. And this is a negative charge here. The positive charge of the salt bridge goes here. Your salt bridge, from the word itself, contains salt, and salt are usually soluble. Okay, so the role of the salt bridge is to make sure to maintain the electron neutrality, because in the electron transfer, one solution will be negatively charged while the other solution will be positively charged. So to prevent that from happening, you have to put the salt bridge. And as they say, a voltaic cell is made up of ABC, anode, bridge, cathode. Okay, so I'm just trying to review your Gen Chem because most of the questions that I have is just the Gen Chem level. Because I just want to make sure that when you take the exit test, okay, I'm reviewing you for your Gen Chem or the inorganic type questions and analytical chemistry. Because as Dimo said, that's the courses that's always problematic. When you say problematic, their average is always below the national average. And he always tell us that PChem and Orgo is always higher than the national average. Okay? So if you're going to recall, the way that you're going to put this cell diagram, as they call it, is like this. So this is the anode, this is the cathode. So the salt bridge is these two lines. The single line that you have here is just a phase boundary when they have different phase. So you have here cadmium, okay, producing cadmium nitrate or cadmium 2 plus. And then here you have silver nitrate, which is silver plus to produce silver. So if you're going to look at this, this is also like this reaction that you have here. Because if you're going to write the overall cell reaction here. So it's just cadmium plus 2 silver producing cadmium 2 plus and 2 silver metal. So I'm just going to put the aqueous here, the solid here, the aqueous here, the solid here. You still remember that? So this is the so-called cell diagram. Now, I'm going to put here how they were able to get this reduction potential. If you remember, you have the so-called reduction potential table. Now, you may ask yourself, how were they able to get those values that are listed in the reduction potential? So how they do it is each of the metal and the respective electrolyte, they measure it against an SHE, the standard hydrogen electrode, and that is usually a platinum with a hydrogen on it. So this is how the setup looks like. So a hydrogen and an H plus. And what they did is they set the value of the SHE as equals to what? Anyone? What's the value of the SHE that they set? What number? Wondering who's absent. Someone absent. Jennifer and Cesar. So what's the value that they set for the SHE? Anyone? If you recall your Gen Chem 2? What's the value that they set for SHE? Usually they set a value of 0. Okay? Now, why did they set it to 0? Anyone has an idea why they set SHE equals to 0? So what's the nature of the redox reaction? If you're going to look at the redox reaction, usually you're going to get a potential that is either positive or negative. By setting the value equals to 0, so whatever's the reaction, it's always equals to 0. And the idea that they have there is the metal that measured with your reduction, with your SHE, will either give you a positive or a negative value. Okay? Because what happened there, if you're going to look at reaction, the reaction that you have would be like this. H2 plus 2 electrons will give you 2H plus. No, I think that's not how it is. It should be H2, 2H plus, that's give you 2 electron. Or if you're going to do it, you can have it like this. So both of them can have a value of 0. Whether you reverse the reaction or they are in the reduction form, the value that they have is 0. So it's easier for the other metal that they're being measured with to get its reduction potential. Now, what do you know about the reduction potential? What's the rule? So if I have it this compared to this one, which one is reduced, which one is oxidized? What does the reduction potential tells us? So reduction potential tells us the higher the reduction potential, it will remain in the reduction form. The one with the lower reduction potential will undergo oxidation. So if I'm going to react these two, which one will happen in the anode? And which one will happen in the cathode? What is the role of your silver? Is it an anode or in the cathode? Is it will it serve as an anode or a cathode? So silver has a higher reduction potential. So what does it? What's happened to it? Is it going to undergo reduction or oxidation?
It'll undergo reduction.
Okay. So this is where what will happen in your so that reaction will remain as is because that is reduction. Now the one that has a lower reduction potential, that will undergo oxidation. So the reduction potential table, it's a useful tool to predict which one undergo oxidation and which one undergo reduction. The higher value or the more positive value will undergo reduction, while the more negative value or the lower the value, that will undergo oxidation. Okay? And the way that we have there, if you could remember, the potential of the cell is usually equals to what? How did you learn it from your Gen Chem? Did you do it like this? Or you just do it like cathode minus anode? What's the difference between the two? Is there any difference if we're going to look at the cell potential between the two? The answer is no. But you might ask yourself, why do I have a positive sign here and why do I have a negative sign here? And right now, for me, so that students will not confuse, I just ask them to use this one. So what does this mean? So usually what you're given is the reduction reaction. And all you need to do is just look at the potentials that you have there and use it as it is. So if I ask you, what is the cell potential of silver and copper voltaic cell? Okay, all you need to do is 0.799 minus 0.3399, 0.339. Now you may ask yourself, now how is this different from here? So what's the cell potential of these this battery that's made up of silver and copper? So if we're going to do it, you have 0.799 minus 0.339. So you have there 0.46. Now, how is this going to be the same with that one? So usually when you make it into this one, this is what? An oxidation. What happened? You change the sign. So if you're going to make it into an oxidation, it becomes negative 0.339. So if you're going to use this one, the value that you have is 0.799, okay, plus negative 0.339. And you may ask yourself, why negative? Because we reverse the reaction. But if you're going to get the value here, it will still give you 0.46. But for me, if you took the Gen Chem with me, okay, the way I do it is for students to remain what we call focus. You just use what's the given reduction potential. And the thing that you need to remember, if it's a voltaic cell, your cell potential should always be positive. So the way I ask my students, just use it like that, and then identify what is the cathode and what is the anode. So since this is the cathode, you just subtract the reduction potential of the anode with it. Okay? So we have here Nernst equation. So we have this so-called cell potential and the standard cell potential. So how do you distinguish the two? The standard would have this degree sign. So when you have a degree sign, that means it is a standard condition. And when we're talking about standard condition, usually 1 molar, okay, at a particular temperature and pressure. Now, how is this different from this? So if the concentration is not equals to 1 molar, then you're going to get a different cell potential. But if it's equals to 1 molar, what will happen? The concentration that you have here, 1/1, will just be equals to what? What is ln of 1? Anyone? What is ln of 1 equals to?
0.
0. So if this is equals to 0, so everything will be 0. So in that case, your cell potential is equals to the standard cell potential, but that's not always the case. So if that's not the case, that's where Walter-Nernst equation comes in. So if you're going to simplify this one, I hope they put it here. So this just becomes here. And if you're going to look at this log, and you could say, why A? A is for activity. If you recall in chapter or lecture 7 or chapter 7, we discussed about the usage of activity instead of concentration. So this is activity of the product raised to B over activity of the reactant raised to A. Okay? And if you're going to look at in terms of the reaction that we have, we can have it in terms of this. The positive potential minus the negative potential. So I maintain here the one that I told you. You just use whatever is given to you in terms of the reduction potential. And if you're going to look at this, they are both in the reduction reaction form. So when you say positive and negative, this is just more positive, and this is the one that is more negative. Okay? So if you're going to look at this, you will end up with this equation. So Q here, that's just the concentration of your products over the reactant. Why did we use Q, not K? K is usually a system in equilibrium. Q is at any point during the reaction. That's the difference of the two. But they are the same in the sense that it's a ratio of the products over the reactant. And if we're going to look at the thermodynamics, okay, so we have this. how delta G is related to delta H and delta S. So this is the free energy that we're discussing earlier. And how we relate K with the delta G. Okay? And how we end up with this. So if we go back to what we have before, so usually if your Q is equals to the K, what does it mean? Your E is equals to 0. So this happens at equilibrium. Or the way we do it, at equilibrium, E is equals to 0 and Q is equals to K. So what happened here, you end up with this thing because this becomes 0 and this becomes K. Okay, so the way that you're going to do is you can move this side on the other side, giving you this thing. And if you want to get the K, you end up with this value. I think I have some equation that some problem that I have here at the end. Okay, so if you're going to look at the Nernst equation, as we know from thermodynamics, on how we end up, okay, with this equation. So delta G is equals to the standard delta G plus RT, L, and Q. And we know delta G is equals to NFE minus NFE. So if you're going to replace the delta G here with NFE, this is the expression that you have. And what happened? You're going to divide all by NF, or you could say negative NF. So from that, you end up with this, this, and this one. And this is your Nernst equation. If you're going to simplify this thing here, you end up with that one. If I'm not mistaken, if it's an L and Q, I think you have some 0.02 something here, 254 N. I think it's in the next slide that we have here. Okay. So here now, how are we going to solve for the E here? So if we have this system, how are we going to get the cell potential for this? So the way that we're going to do that, we can do it the long way or we can do it the short way. Okay. So the way that we're going to do it is we need to know what is this, and this one. So this is the reduction potential. So I can put the reduction potential here as this one is equals to 0.799 and this one is negative 0.402. So you can ask the question, which one oxidized, which one is reduced. Okay. So I can do it like the long way that we have. And if we have that, we have to what we call do it one by one. So I can have E plus and E minus. So what is my E plus here? The silver or the cadmium? I'm going to do the long way and then later on the shortcut. Okay? What is my E plus here? The silver or the cadmium? So my E plus is the silver. So I can put this as this, okay, minus 0.05916 over N. And that would be the log of what? Is it silver or 1 over silver ion? How will I'm going to put this one here? So as you're going to see, you don't have an ion here. So I could just put this as 1 over silver. Or if I'm going to put it based on the reaction here, there's 2 silver that is involved. So I have to make it as squared. So I'm going to replace this with 0.799 time minus 0.05916 divided by 2 times log of 1 over, what's the silver concentration that we have? 0.5. So I could get there the E plus. So I want you to calculate that when I set up the other one. So for the E minus, the same thing. So I can just use the negative 0.402 minus 0.05916 divided by 2 and then log. What's the concentration of my cadmium here? 0.01 times log. Then what would be the corresponding E plus that I have, E minus that I have there? So what's the E plus? Is it 0.5 or 0.05? I just want to make sure. It's 0.5. So what do you get on this side when you do the operation for this? Because you're going to subtract it with the whole thing here, 0.799. Point 0.05916 divided by 2 times log of 1 divided by 0.5 squared. So I get here, I'm not sure if you get this thing also, 0.0178. So I get there the 0.799 minus that. So I get here 0.781. Did everybody get that? Now how about the other one here? Negative 0.402 minus 0.05916 divided by 2 times log of 0.01. So log 0.01 times 0.05916 divided by 2. What do you get on this side? Is this correct? I think you have to do it like this one. So that means I'm wrong here. So if I'm going to do it 402 minus 0.05916, 2. So everything is in the reduction form. So this is my mistakes. So it should be like this. So if we have it like that, log of 1 divided by 0.01, that's 2. So negative 0.402 minus 0.05916. So this is just equals to 2. So if that's 2 and 2 here, so this is the value that you have. So you end up with negative 0.461. Okay. So to get the value that we have here, 0.781 minus 0.461. So this is equals to, what do you have? I get here 1.242.
I got that too.
You
I
got
got
the
the
good.
image.
Now, I can make a shortcut out of it. Okay. So what is my shortcut? So I have here E, and the way that I do it here is the E cathode minus the E anode to give me my standard E. And then I'm going to put this thing 0.05916 divided by 2 and then log. What do? I'm going to use this reaction here. So which will I put in the numerator? I can put the cadmium there because that's the one in the product, and the silver here. So if I'm going to do that, what will happen? So I have a 0.799 minus negative 0.402. Okay. And then this whole thing here, log, what do I have here? The 0.01 over 0.5 squared. And that should also give me the same answer. So the remaining stuff that we have here is just more calculations. How the cell potential is related to your delta G. And I just took it directly from my Gen Chem 2 notes. So if you're going to look at it, if you have a galvanic cell, it's spontaneous in nature. If it's electrolytic cell, it's non-spontaneous. If your system is at equilibrium, you have a dead battery. Now, synonymous to this, the cell potential will be positive in a spontaneous cell. The free energy is negative. That's why the battery is doing the work, right? So the battery is the source of the energy that will do your work. Now, if you have a non-spontaneous reaction, you have a negative cell potential and you have a positive delta G. And it will not run unless you apply energy to it. Now, in terms of K, okay, the spontaneous one will have a positive, or we could say more than one K, because you have more products compared to the reactants. Now, for the non-spontaneous cell, there are more reactants compared to the products because the reaction is not proceeding. It's not happening spontaneously. So this is how they are related. So the other stuff that we have here will, after we took a break, it's just problem solving, similar to what we did earlier. Okay, so we'll just took, what time is it now? 10:35. So just a 5-minute break, and then we're going to resume, and then we wrap up everything. Okay. So this is just straight from my Gen Chem 2 questions or lecture slides. Okay. So we took a 5 minutes break, and then we're going to resume again. So see you in 5 minutes. Okay, so let's continue. So you're asked here, what is the equilibrium constant for the following reaction? Okay, so ideally, this is how you're going to get this. You need to get the self potential first, and then from that, you're going to get the ln of k. So if you're going to look at the self potential here, you need to know, okay, what's the reduction potential of Fe2 plus going to Fe and silver plus going to silver. So we need to get this. So if we're going to do is we're going to need a table. So Fe2 plus, trying to look at my table here. So that's negative 0.45. Silver would be where is silver? 0.80. So this is negative 0.45 and this is 0.80. Now, as you could see here, this is our what? Cathode, and this is our anode. So the way that we're going to do here is the self potential is equals to 0.45 minus 0.80. So what is that equal to?
Negative 1.25.
Okay, so that will be negative. So what does it tells us? What is the type of cell do we have? Is it a voltaic cell? Do we have a voltaic cell?
I think this is the Giovannic cell.
Okay.
This is smaller than 0.
We have a electrolytic cell. Why? Because we have a negative value. So what does it tells us? What will happen to your K here? So if we're going to look at this, this is how this looks like now. So if we're going to rearrange it, it will be 1.25 times 2 divided by 0.0257. And then you have ln K. How do you remove ln? We remove
You
ln by getting
E both
whatever
sides,
you
right?
get here. That's a negative value. So E so negative 1.25 times 2 divided by 0.025. So what is K equals to? I get something that is to the negative 43. What value do you get? What's the value that you get there? I know it's times 10 to the negative 43. So 5 point, maybe 5.67. So what does it tell us? Does this make sense? Does the value make sense? What does it tell us? It's very, what, big or small?
It's very small.
It's very small. Now, does that value make sense? Since this is a negative value here of your cell potential, so that means your reaction will not be spontaneous. So in that case, you have more reactants than products, hence your K is so small. Remember, that's how your K ratio looks like. But here, this is much larger compared to that one because you have a very small number. So this value makes sense. Okay? Question.
Just real quick to clarify, electrolytic, does that mean you have to add energy to the system?
Yep.
Okay.
So you have to apply energy to make the system happen. So you have to apply energy here to make this reaction happen. Without any energy, this reaction will not take place.
Right. Hence
So
the super small K value then, right?
yeah. So if you're going to look at this reaction is non-spontaneous. But if you reverse the reaction, that reaction is spontaneous. Now in this case, you do not set the cathode and the anode. It was given to you that your Fe2 plus is your cathode and your silver is your anode. Okay? So you're not the one to set that thing. It was given to you which is the anode and which is the cathode. And you may ask yourself, how? How was it given to you that this is the anode and this is the cathode? Because this is an Fe2 plus. So this is the one that is reduced. It's given there. And this one is the one that is oxidized. Okay? Now, how about this one? You're asked here if the reaction occurs spontaneously in a given set of concentration. And again, you're given which is oxidized and which is reduced. So all I'm going to show to you now is what's the reduction potential. So if you're going to get the reduction potential, you have to write everything in reduction form. So we already know this as equals to what? Negative 0.40, right? Or 45? Is that the one that we have there? Yeah, that's 45. And the other one, that's cadmium 2 plus 2 electrons. So I have to look at my table. So usually you'll be given the value for this. Because if you're not given the value, even I cannot solve that thing. So cadmium would be 0.40, negative 0.40. So how do we get the E cell here? Is it like this? Or the other way around?
It's the other way around.
How about the others? Is it the one that I written or I have to reverse the two? Remember, as I've told you, the cathode and the anode is given there. So how will I write the E cell? This one. Is it like this, or I'm going to put this one in front and this one behind? Anyone? You can type your answer, each of you, as written or swap. Did I wrote it correctly, or do I need to swap the values? Where's the others? So if we're going to look at this, okay, this is your Fe2 plus, and this is the one that is reduced. So that's the one in your cathode. And this is your cadmium, the one that is oxidized. So it remains as this one. So you're going to get what? A 0.05. Am I right?
That's right. Yeah, I was wrong.
Okay. So this is the E cell, but the question now is, will the reaction occur spontaneously given this concentration? So you have to use the Nernst equation. So I have here the cell potential equals to the standard cell potential minus, how do we do that? 0.0916 divided by 2 log of cadmium over Fe2 plus. So we use this here. Now the question, are the concentration ratio here enough to make this value here positive? If that becomes positive, then you could say it will occur spontaneously. So let's see. So I have it here. So what do I have? 0.01. And the other one is 0.60. Right? So what is the answer? So usually, what do I get here? Log 0.01 divided by 0.6. I get a negative times 0.05916. Is this what you get?
Yeah, that's what I got.
So we could say that's a 0. Okay, so 2.5 times 10 to the 3. Negative 3. So that means at this concentration, you can already have a spontaneous reaction. So usually what that's what they do. They just adjust the concentration to make a non-spontaneous cell into a spontaneous cell. And in some instances, in the last example that I have here, They even use the same species. They even use the same metal. The only difference is the concentration. Okay, because if you're going to look at this, if we're going to use this value here, so this is what the Nernst equations look like. So which one will be 0 in this equation? Which one will automatically become 0? Anyone? If I'm going to make this in a question, in the Nernst equation, when we have a concentration cell, which value is automatically become 0? So I could put this A, B, or C. What is your answer? Maybe I'll ask you to answer, each one of you. Where's that Jeopardy sound? Yeah, please write your answer. So if I'm going to ask a question like this one, in the Nernst equation, if we have a concentration cell, which of the following will have a value of 0? Start your answer now. No, just A, B, C. Don't get away from the thing.
Did you know you can?
What do you mean by ABC? Do we what to put in the bracket?
There. See that? Doesn't want to do something. And the answer is letter B. Okay? Because if you're going to look at this, what will happen here? Your E cell, what we call standard E cell. I don't know why I cannot write with this one now. So you have the same cathode and anode. Since you just have the same sink, you're going to have the same value. So that one will automatically become 0. So everything will depend on the ratio that you have here. Okay? I don't know. My pen is not working anymore. Maybe I'll stop the share and then leave it again. So what do we do? What do we have here? Is it 1 over 0.1 or 0.1 over 1? In my last slide, and I don't know why this doesn't work. I just try to disconnect it and then connect it again. So is it 1 over 0.1 or 0.1 over 1? How are you going to write the values that we have on this side here in letter C?
1 over 0.1.
Okay, it's 1 over 0.1. Unfortunately, I don't know what happened. Ah, keep. This is the last slide and you're already on the last slide here. So if you're going to do it here, this is 1 and this is 0.1 and this one automatically becomes 0. So you're going to have a value here. And that would be equals to what? Did you get this? Or around 0.03. Did you get that value? It should be positive, I think. Log of 10. Yeah, I think it's, I'll try to make sure. 1 divided by 0.1. Oh, I think we're wrong here because this will be a negative, right? Because if you're going to look at here, zinc producing zinc 2 plus, which is 0.1, and zinc 2 plus, which is 1, producing zinc. So this is the one that is canceled. So this is the one that is 0.1 and this is the one that's 1.0. So my mistake. So if we do that, log of 0.1 will give you negative 1. 8 times 0.05916 divided by 2 will give you this value. Okay? So that's what we call the right one, 0.1 over 1. And I hope by showing you the reaction here, the equation here, you should able to see why. My mistake. Okay? So question, before I ask you to show up your pace.
Yeah,
This is our last meeting.
I thought the earnest equation end up with ln of the constant. How do you convert it to log?
If you got, what do you say, Hanbo?
I mean, the equation is like uses ln, right?
There's an ln on that, but if you have an ln, you're going to have a different value here.
Oh, okay, got it. So you basically convert it right there already. So that's
Yeah.
why you're using a log. Oh, got it.
If you use an ln, make sure you use the corresponding value that's here. You can use that, but you're going to have the same number.
Got it. Thank you.
Question before I discuss our lab this week. So we're going to do 2 batches in our lab. So the way that we're going to do, so those who are supposed to be there last week, you're going to be, let's say 1:20 to 2:30. And the next one is 2:30 until we're done. So the way that you're going to do 1:20 to 2:30, you divide right away yourself into two, and one would prepare calcium 2 plus, while the other one will prepare magnesium 2 plus. And then we're going to measure your, as a sample, the water that you use in experiment 7. So this is the AAS. Now, I would suggest the next batch that's supposed to be here this week, be there at 2:30, okay? So what will happen is, I hope that the first batch will be done. If not, then just wait outside, okay? Because what will happen here is the AAS, we have 2 lamp. I have to turn it on and then turn it off and then turn it on and then turn it off. And then when the fluoride come here, by 2:30, you're going to prepare different fluoride, and then you're going to analyze different samples. So both experiment, okay, will just involve what? Calibration curve. So you might have it like that. I think the other one would be like this. And then from that, you'll be able to find what's the concentration of your unknown. So that's how the experiment is to this week. And we will only have one quiz for that. And the quiz is on calculation. So you have an idea now what the quiz is all about. So that's our last meeting in person. Okay. So question. So the ones absent is Jen and Cesar. I don't have any students in trouble of failing the course, unless of course you don't show up in the third exam and the final exam. Okay. I only have one student who's not submitting any or always delayed in his lab report. But other than that, I don't have any problem with any of you. Okay. And I'm hoping that I think the lowest grade would be a C or better. But I have some students who are in A as of this time. And then I'm just going to adjust everything, whatever we have. So I posted already the assignment for this. If you want to submit early so I can post the answer key, it's up to you. But I'm going to make available the problem set already as early as today with the answer in the problem set. Because remember, you have a third exam next week that covers chapter 10 until today. So the titration that you have until the one that we have today. And then we have, what's your decision? Are you going to take the problem solving exam on Wednesday next week, and then multiple choice all in the November 23 exam? What's your decision? Hmm?
What would the what would the allotted times be if we were to split it up?
In the Wednesday, we're going to use the laboratory class. In the Monday, I'm going to give you the whole morning, but it's all multiple choice. I'm going to give you the whole 9 to 12. That, as I've told you, since I'm worried about your scores in the exam, in the Blackboard part, I want to have like an insurance that if you mess up the multiple choice or the Blackboard part, I can always use your problem solving exam.
So you're saying for exam 3, we're gonna have multiple choice on Monday.
You also, the exam 3, you're going to do everything in one meeting. The
Okay.
Monday time that we have
You're
next week.
talking about the acted exam. The
Okay.
final.
So the exam 2 is just like what we have before, the first and the second exam. But the final exam, originally, the plan is all multiple choice. But based on your scores, I'm worried. So what I'm trying to do is, I have some backup plan on myself. That's why I'm giving you, since we don't meet Wednesday next week, we're going to utilize the 120 to 420 time to utilize the problem solving. Or maybe if you want, I'll give it to you at 12 o'clock and then you give it to me by 5 o'clock, because it's a problem solving.
So I just want to be clear. What if it's the for the final exam? What if it's the other way around? What if a student does poorly on the written part but does well on the Blackboard? Could it go both ways?
No, the
Like,
thing that I'm going to do is, if I'm going to follow myself, the final exam should just be the Blackboard. That's how it
Mhm.
is every semester. But what happened is, the scores are really horrible. Okay, so I still give the students the what we call the this problem solving exam. And the way I try to do it is, I can go a 50-50% portion of the Blackboard and the thing.
Okay. Okay, I understand.
Anything that will end up as a higher grade. So if the Blackboard is already, let's say 80%, okay, and if I included the thing, he will become 75%. So I just skip the 80%. It's additional work on my part, but at least I'm what do you call this, a little bit satisfied that I give the students all the opportunity to improve the grade. So if you get a 90 in the multiple choice, okay, and you get a 100 in the written exam, so I'm going to combine them to give you 95. So whatever combination that will give me the higher grade. So I still have the option just to stick with the Blackboard. But as I've told you, every semester, I don't know. Because the thing is, it's also what we call, the way I'm trying to do is to prepare you for your exit exam. Exit, you are required in the department to take this exit exam. Okay. But remember, the setup that we have before is a face-to-face. So I don't know how you're going to perform. I expect at least in theory to be better, but based on the thing that I have right now, it's not good. I mean, not for you, but the other courses that I have. But I'm hoping you're better because you're not going to use the respondos. So I'm willing to give you the whole time now, because earlier I'm still hesitant to do it. But I think maybe just my Christmas thing to you. So if you opt not to take the problem solving exam, if you don't do well in the Blackboard, then I can't do anything. That's why the way I try to do it, additional work for me, but at least I just don't want to disturb you after November 23.
Okay, well, my vote is I say yes. We do both, but that's only me. So we'll see what the
Yeah.
class says.
No, that's why this is the thing. We're going to push through with the problem solving on Wednesday next week. If you don't take it, then it's just for me. You're sending me a message that I'm just going to base the final exam in the blackboard. And if you don't do well, then you don't have the right to ask me to get the problem solving exam. That's what it means. I mean, you blew up your opportunity to take it if you don't show up on Wednesday. Okay, so that's the one in the next week, because this week we have a last meeting. We're going to do two experiments. So the one that's supposed to be there last week will be the first batch 120, and the one that will really be here this week 230. Okay. This is our last meeting in Zoom. So you can show up your face now. Although I'm happy that at least we have interact in the lab, because it's worse in my other class. I just see them in Zoom. I don't see them in real life. Okay. So what do we have? The third exam we have it November 16. Final exam blackboard, that's November 23. So the final exam for the problem solving part, that is November 18. Okay. So today we're going to do, this week in the lab, we're going to do experiment 10 and experiment 12. So our lab will be done this week. So question. I just have, I told you, we have one lab quiz this meeting. It's all calculation. Really don't show up? So I would like to thank you for everything. At least every Monday we're here. Okay. I know it's not the best setup that we have, and then we didn't even start correctly because our first Monday meeting, there's an outage in Zoom around the US. So I hope you have learned something. I hope that it might be useful. And I'm also thinking, if you want, just to some of you, okay, if you want an additional point. So if you do this report, I'm going to give a +2 if I'm happy with the report. If not, if you just submitted, I'll give you a +1 in your total grade, in your final grade. Okay. So this is the thing, is something to do with the election. Okay. I want you to write something about how the forecast, okay, is correct or wrong with the actual results. Because I have some friends who are statistician. I told them, now, after this election, no one will going to believe in these polls, because they expected the blue wave and it didn't happen. Okay. So if you want to do like that, it's just like you compare what has been predicted by this survey and what is the actual results, and then maybe reason out why they don't match. What are the factors that make the actual result different from the predicted survey? So this is just applying what you learn in statistics and how you apply it in real life. So if you're going to give me a report on that, if the report is good, I'll give you a +2. So if you end up with 87, the report is impressive, you will get a final grade of 89. If you submitted and are not satisfied, maybe a +1. Okay, so it's up to you, especially those who aim to get an A. Okay, so this is your chance to improve your grade. So this is just like comparing the predictive survey versus the actual results in the election, and what makes it wrong and what makes it right. So maybe to some of you, if you want to focus on a particular state, especially if you come from a particular state, it's good. So all you need to do, these are the surveys before the election, and this is what the actual score during the election. And then you're going to put some reasons there why they match or why they don't match. Okay? Because they expected the blue wave, but it didn't happen. And I'm also giving you +10 in your final exam if, okay, I don't know if you'll be happy, the present president will concede. So if he concede before the third exam and the final exam, you have +10 in both exam. But I doubt if he ever concede. So I would like you to do also the student evaluation. Okay? Please do it because I never been in this situation before. So I want feedback. Looks like we won't get the 10 points. Yeah, that's why I'm confident to give that bonus to you. I also gave it to my class and they said, never mind. But that's the thing, okay? So we still have an opportunity. Some of you still has an opportunity to meet me personally this Wednesday. So if you have any question, then you can ask during that time. So we still have an assignment. So I don't know. You want the assignment to be submitted by Friday so I can make the answer key available? Because even though we don't discuss the assignment, I always posted the answer key, okay, to guide you. Okay, so let's make it Friday, the deadline for the last assignment. That last assignment has been posted already. Okay, so I can put the answer key for that. Okay, and if ever you have any question, feel free to email me. We can always have a Zoom meeting. Usually my I didn't able to tell you the office hours that I have. It's from 3 to 4. Okay. So thank you very much. Okay. I hope I don't know how to do it. I hope you're doing well, but I cannot say it because me myself, I'm really burned out right now, to tell you frankly. Okay. And if there's any way I can be of help to you, just let me know. Okay, especially if you feel that you want a much higher grade, because the thing is, I'm just going to give you something, maybe another exam, but as much as possible, if I can make the lowest grade as B-, I'll try to do so. Okay, but I cannot give everyone an A. Okay, the A is if you're really on top. I can only give you an A if you're an A minus, and then that's the opportunity for you to become an A. Okay, but to improve your grade, let's say if you're in the B range to make it a B plus, then there's always an opportunity. I already give you that +2 opportunity. It's just easy. Okay, so the actual survey, the predictive surveys are still available. You can look online. There's a lot of surveys that being done. If you want to look at the general election, the total thing, it's much better. But if you want, some of you, I know, you have your own specific state. Okay, so maybe you can focus on that state, and then you can tell why is it, because even now all my friends, I already told them, how can we tell our students that statistics is useful in prediction if the result is messed up again? Because I already told them statistic is useful until 2016 results shows that's not useful. And again, I think the trend is also like that. So it's always a problem. I don't know why. Okay. So the question that being asked now, will you still believe in polls in the future election? Okay. So there was really surprise, because I think in terms of the senators, so some that they predicted to lose, they won, like Lindsey Graham. He was predicted to lose, but he won. So that's the thing that I want you to look at, because it's really within